Let's get started here. So midterm grades have been posted. For the most part, you guys did pretty well. I'd say I think the class average was mid 80s, which is good. Left skewed distribution. So. If you have any questions about the exam, you want to see yours, you can come during office hours. Some of you guys already took a look at your exams, but if you missed the chance to see it this week, just send me an email next week so I know to bring your exam to office hours. Just because I don't want to have to bring the entire stack every single week. But I'd be happy to let you see your exam. Okay, so we're going to continue on in our course, and we are going to enter chapter 7, which is all about kind of our introduction to inference. Okay, and if you recall, I said, what was kind of the big picture idea of statistics?
Professor, can we turn down those lights on the front of them?
Oh, yes. Give me a second. Okay, so if we talk about the big picture idea of statistics, we said that part of statistics is all about making conclusions from limited data. So, there exists some kind of population. The population, this thing is too big to observe directly. And so instead of trying to survey or interview every single person in the population, what we do is we take a little piece out of that population, and the thing that we can observe, this is called a sample, right? Too big to observe directly. So we select a sample from the population. Ideally, our sample is representative. Representative of the population. Okay? And if we observe something in our sample, perhaps what we observe in our sample can then give us an idea of what exists in the population. Okay, and so this idea of looking at a sample and then making conclusions about the population, that is inference. Okay. Oh yes. Hope you all had a good weekend, and happy Valentine's Day. Thank you, thank you. And great President's Day by Couch or something. All right. Okay, great. So so this is kind of the big picture idea that we have, and then and so we want to. There's a few things we need to cover in order to kind of build the foundation for doing this this idea of inference. Okay. Okay. May I just want to make sure I can flip to the next slide here. Okay. All right. So our so again, just a few key terms. Okay. So our population. This is everyone relevant to the question we wish to answer. So, let's say the question is, what percentage of Republicans in South Carolina, because they're having a primary coming up, right? So we'll say, what percentage of Republicans in South Carolina support Donald Trump? Okay? So let's say this is the question we wish to answer. Okay, and the only way we're going to, I guess I should say, what percentage of voting Republicans, okay? And the only way to actually answer this question is on the day that the primary election takes place, okay? So the true answer only comes on the day of the election, okay? And that is because everyone in the population, everyone who votes, that is the population, okay? The population is everyone who votes on the day of the election, okay? Population is all voting Republicans who vote on election day, or whatever, the primary election day. It's still called an election, right? Primary election day. Okay, this is the population. Okay, this is the idea, this is what people are interested in. Okay, and so until this day happens, news organizations go out and they survey people, okay, because they have no idea who's in this population, okay? So until election day occurs, okay, news organizations survey people to get an idea of, this answer here, right? To get an idea of what will happen on election day. Okay. So the people that they survey is the sample. The people they survey. So here's our this is one key term, population. The people they survey is the sample. Okay. number that they want to know about. This is the parameter, okay? The sometimes called the population parameter. Is the quantity they are interested in. They being the news or people into politics, whatever. Okay. You know, because we can't observe the population directly, we have to settle for observing a sample. And so the corresponding value from a sample is known as the sample statistic, okay? The value that corresponds to the parameter in the sample, parameter, is called the sample statistic. Okay, so, you know, I just picked this question. I could have easily just said, you know, what percentage of voting Democrats in South Carolina or any other state in Nevada support Bernie Sanders or Hillary Clinton? But anyway, so if this is the question that's being asked, then the population parameter in this example would be percentage of voting Republicans that support Donald Trump, okay, in South Carolina that support Donald Trump. And then the sample statistic would be the same thing, except it's the percentage of our sample of voting Republicans in South Carolina that support Donald Trump. So let me, you guys have this? I'm gonna flip to the next slide and we'll just define it. So let's say, okay, so this time we'll change it and we'll say, you know, so here's our question. What percent of, we'll say, voting Democrats in Nevada support Bernie Sanders? And last I heard, it's very close in Nevada between Sanders and Clinton. So, okay, so the parameter, this would be the percentage of all voting Democrats in Nevada that support and then the statistic is the percentage of the selected sample. Okay, and when you select your sample, it's of voting Democrats in Nevada that support okay, so they're parallel quantities, but one comes from the population and the other comes from the sample. Okay? So, so if I say, so let me just say this. So I select 200 random people, and we'll say 105 said they will vote, I'll say random Democratic people, or will vote for Sanders. Okay, so my proportion, the proportion is 105 divided by 200 is 0.525. Okay. Is this quantity, 0.525, is this a parameter or a statistic? Okay. Does it come from the population or come from a sample? Yeah, it comes from a sample because it says I've selected 200 random Democratic people here. Okay? So this is a statistics, sample statistic. Okay, because it comes from a sample. Okay, and so in this case, we would say we indicate this as P hat. We put the hat over the P. There's this little cap here, this little roof, to indicate that it's a sample. Okay, so this is called P hat, and this indicates that it's a sample statistic. Okay. On the other hand, the percentage of all voting Democrats that support Bernie Sanders, that quantity is P. This is the parameter of the population. Okay. Does that make sense? All right. So we want to get into this idea of a sampling distribution, okay? So let me just make sure you guys have this written down. And I'm going to try to explain how we're going to build a sampling distribution here. Let me just close out of this. Okay, so when we're asking what kind of conclusions can we make about the population based on a sample, a lot of times we want to know, well, if I take a sample, is this going to give me a good idea of what the population looks like? All right, and so just to kind of illustrate this point, okay, let's say I've got this big bucket of M&Ms, or actually we'll do Reese's Pieces candies. Okay, and Reese's Pieces, they come in 3 colors. There's brown, yellow, and orange. Okay, and so let's say we got 100 pounds of Reese's Pieces candies in here. Okay, we've got a whole lot in here. All right. Decided to spend your last month's paycheck all on candy. It's a terrible idea, but it's for the sake of statistics, guys. Okay, so let's say you went through the trouble and you counted every single candy in there, okay? And you counted exactly how many orange pieces there are, okay? So you have counted every single piece. Single piece of candy, and know exactly the percentage of orange pieces. Okay, so let's say, let's just say for simplicity, say there are exactly 30%, or 0.3000. The proportion is 30% orange in the tub. Okay, so maybe there's 100,000 pieces of candy and exactly 30,000 of them are orange, okay? All right, and now what we're gonna do is we're gonna mix this up, okay? And we're going to take a scoop. How do I draw a scoop? Okay, we're gonna take a scoop of candy out, okay? And each scoop will have exactly 100 pieces of candy. So we scoop out okay. So what 30% here, this would be the, is this a sample statistic or a population parameter? This is a parameter, right? This is something that is defined by the entire population, which is our entire population of Reese's Pieces candies. So here we have population parameter, population proportion is P equal to 0.30. Okay? We're going to scoop out 100 pieces of candy. How many do you think are orange? 30? Is it necessarily going to be 30 pieces of orange candy? No, we could get 32 orange pieces of candy. We could have 27. So, okay, so we're going to scoop out 100 pieces of candy. Let's say we get 32 orange pieces. Okay, so then our sample statistic, our sample proportion is P hat equal to 0.32. 32 divided by 100. Okay, so my sample of 100 random pieces of candy is 32% orange. Okay, let's say I do this again. Okay, 100 pieces of candy. How many orange pieces this time? 26 orange pieces, sure. Okay, so P hat, 0.26, okay? Another one, okay? Okay, and 100 pieces, and let's say we get 30 orange pieces. Okay, and we'll do this again and again, right? I wish I had DJ Khaled. Another one, another one, another one, right? So we'll do this over and over and over, and every single time we're going to record how many, the proportion of orange pieces that we get in our sample, okay? And we're going to keep track of every single one of these P hats, okay? We keep track, so we repeat this over and over again. Okay, and we keep track of all the P hats. Okay, so we can do this via computer simulation, okay? I'm going to come here. Let me go on the internet. Okay. Reese's Pieces. Sampling distribution. Okay, so I'm going to do this first one. It's going to draw this, and it's going to animate. So it's dumping out all of these. It's getting a bunch of yellow and brown pieces, some orange ones, okay? and it's going and it's going. Okay, and it got 26 orange pieces. Okay, and so we want the proportion of orange. Okay, so that's going to be 26% orange, and it puts a dot right there. Okay, and I'll do it again, and so you can see. So it's mixing up this giant thing of candy, and well, it's just a simulation, so not actual candy involved. And we're gonna count how many orange. Oh, we got 26 again by coincidence. Okay, I'm gonna turn off the animation, and this will speed things up a little bit. Okay, so we got 25 orange pieces, so 25% orange. Okay, this one got 35 pieces, so we have 35% orange. Okay, and we can just keep doing this, right? Another one. Okay. We need the soundboard for that. All right, so just to kind of speed things up, I'm gonna do like 10 at a time here. Okay, so far I've done 6, and this is how, you know, we got 35% one, 32% one time, and you know, these other numbers will do 10 more. Okay, so this adds 10 more dots to the dot plot. Okay, and we'll do this again. So there's another 10 dots. So, you know, occasionally we get 20% orange, and this time we got like 39% orange or something. Who knows, okay? So I'm going to speed this up further. We'll do 100 at a time. So now there's 146 dots, okay? What do you think, what kind of shape is going to emerge if I keep doing this over and over again?
A bell.
Bell curve, okay. So there's another 100. So this is after 646 samples, okay. We're getting kind of this peaked shape, okay. Let's do 1,000, okay. So at this point, you know, the dots have gotten so small that they've kind of merged into lines. But here I'll do 1,000. This is after, so 1,646. Let me, 354, just to kind of get us to an even number. So this is after 2,000. Let's do another 2,000. So with the computer, we can do a bunch of these very quickly. So after 4,000 samples, what does this kind of look like to you? Okay. Yeah, so it looks like the bell curve, or like a normal distribution, okay? And in fact, we have something called the central limit theorem, which says, you know, this is after 10,000 samples. Each one of those samples has 100 pieces of candy, and every single one of those samples we recorded the p hat that we got, okay? And so this is after 10,000 samples. And if I were to do like, I don't know if let's see if the computer might get mad at me. Oh, it did it, okay. You know, 20,000 samples, it generates something that looks very much like the normal distribution. We can overlay a normal curve in blue over it, and we can see that that the lines fit it very quite well. Okay. So let's talk about this. Okay. So again, this is the idea of the sampling distribution. The sampling distribution is the distribution of the different p hats that we observe if we repeatedly take samples over and over again from our population. Okay, so let me write this down. Sampling distribution, this is the distribution of all the different p hats. So p hat is our sample statistic, right? All the different p hats that we can observe, if we repeatedly take random samples from our population. I just want to make sure conceptually that this, this concept of a sampling distribution makes sense. Okay. So we're just, I'll flip back to the previous slide just to kind of reiterate what's going on. Oh, but I'll let you guys catch up on your writing. Okay, so again, we have this big thing of candy, and you know, every time, what we're going to do is we just draw pieces of candy. We count how many pieces are orange, and we calculate the proportion. So we get 34% that are orange in this sample. Okay, we do this again. 24% orange that time, 30% orange that time, 32% orange that time. Okay, we do this over and over and over again. Every time we're going to go to the population, which is this giant thing of candy, okay? And every time we take a scoop, we might get a different number of orange pieces of candy, okay? And so every time we take a scoop, we're gonna get possibly a different p hat, okay? But certain p hats are going to be more common than others, right? 30%, 32%, 28%, these are going to be pretty common. Is it possible that in a scoop of 100 pieces of candy that 50 of them are orange? It's possible, but that's not going to happen very often, right? Especially, if we're stirring up the candy, it's possible for 50 pieces to end up being orange, but that's not going to happen very often. But 30%, 32%, 28%, those are going to happen quite a bit, okay? And that's what we see. If we keep doing this over and over again, what we see is that these values, 28, 32%, they happen quite a bit. 44% happens very, very seldom, okay? So as we generate more and more samples, okay, and we get an idea of what the true distribution looks like, we see that it looks quite like the normal distribution, okay? Okay, so this is the idea of the central limit theorem. Okay, the central limit theorem says, and I have to preface this with, as long as certain conditions are met, okay, the sampling distribution of p hat, okay, which is what we've been generating, the sampling distribution of p hat can be approximated with the normal distribution. Okay, and all normal distributions are defined by two quantities. What are those? To do any kind of normal distribution calculation, you need to know the mean and standard deviation, right? Okay, so the central limit theorem says that, as long as certain conditions are met, the sampling distribution of p hat can be approximated with the normal distribution, okay? This normal distribution will have a mean of, the mean equal to p. So the mean of our distribution is equal to the, what is p? Yeah, the population proportion, the proportion that exists in our population, that parameter, okay? So the center of all the p hats is the proportion that exists in the population. Right? And the standard deviation is going to be equal, and it's just this square root thing. It's going to be p times the quantity 1 minus p divided by n. N is the sample size. Okay. All right, so what does this mean? This means we can ask questions about samples taken from our population. Okay? So we could ask a question like, I'll go to the next slide and I'll write this down, but just give you a second to catch up. Okay, so we can say, you know, giant tub of candy, 30% are orange. Okay, if I take a random sample of 100 pieces, okay, what is the probability that the proportion in our sample p hat is over 0.35? Okay, or I'll say is, I don't know, maybe I'll say 0.35 or more, okay, rather than over 35, but it doesn't really matter. So we'll just say this. Okay, so this is the question we want to know. You know, when I take a scoop of candy out of the giant tub, I might only get 28 pieces that are orange. Okay, but let's say for, you know, whatever reason, I want more orange pieces. Okay, and I can say I'm only going to be happy if at least 35 of these pieces are orange. Okay, this is a ridiculous question, but you know, and this is kind of trivial, right? This doesn't really matter. We're talking about how many pieces of candy are orange, but we might have another question, right? We could say, you know, what percentage of voting adults, you know, what's the probability that the percent, you know, if we take a random sample, what's the probability that this random sample is going to be over 50% in favor of this proposition or whatever, okay? These things can actually make a difference, okay? But here we're just gonna do it with this trivial example here, okay? So this is a question, because it's about p hat, this is a question about that is based on our sampling distribution, okay? So what the central limit theorem says from the previous page, central limit theorem says that the distribution of p hat is normal. Okay, what is the mean again? The mean is equal to p, and the standard deviation is equal to the square root of p times the quantity 1 minus p divided by n, okay? So what is p? Is p 0.35? Is p 30%? What is p? P is our population parameter. So what?
30%.
Yeah, the value that describes our population is 30%, okay? So P is equal to 0.3, okay? Because in the problem says that 30% of the candies in our tub are orange, okay? So that is the quantity, all right? So our mean, the central limit theorem, the mean, we can say P hat comes from a normal distribution with mean equal to 0.3, and the standard deviation is going to be the square root of 0.3 times 1 minus 0.3 divided by n. What is n? Sample size, okay, so what is my sample size? Yeah, I'm taking a random sample of 100 pieces, okay, so this is my n. N is equal to 100. Okay, so this is going to be the square root of 0.3 times 0.7 divided by 100. 0.3 times 0.7 divided by 100. Okay, and I've got to take the square root of this. And I get 0.0458. Let's keep a few extra. 0.045826. Okay, so my standard deviation is sigma equal to 0.045826. Okay. So far, are we okay? Yes?
Why the 30% is the P?
Because 30%, I guess I should say 30% of the candies in the tub are orange, okay? And so the tub here represents, whoops, our population. 30% of the candies in the tub are orange. And that represents the population. This is the big thing that's too big for us to observe directly, and we're just taking scoops of 100 pieces at a time, if that makes sense, okay? And so what we're doing is, based on what we see in this scoop, we're gonna see, you know, how good of a, you know, how close is this, our P hat, going to be to the P that exists in the population. So we happen to know that in this giant tub of candy, 30% of them are orange, exactly 30% are orange. So when I take a scoop of 100 pieces out and I count them up, you know, maybe I get more than 30%, maybe I get less than 30%. This time I'm asking, what's the probability that my sample of 100 ends up being more than 35% orange? Okay? All right, can we answer this question now? Yes, we have.
Is the P what we're interested in knowing?
At this point, no. The P is provided to us at this point in our study, okay? We're starting off in this scenario so that we can move to start asking questions about P. But right now I'm saying, in this situation where we happen to know P, what can we say about P hat? And then after our break, we're going to flip it around. If we happen to see P hat, what can we say about P, okay? But the thing only makes sense if we start talking about P first, okay? Question back there.
You think after this we can do this with a different example? Maybe people.
Yeah, sure, okay. Yeah, I'm sticking with this example just because this is how we describe the building of the sampling distribution, but we can venture out to other types. Yeah, another question.
Is it just the remaining number? So 100 minus 35?
No, that's not how it works, okay? Okay, all right, so at this point we have P hat comes from a normal distribution where the mean is 0.3 and the standard deviation is 0.04, okay? So basically I can just say whatever. P hat follows a normal distribution with mean 0.3, standard deviation 0.045. What is the probability that P hat is 35% or more, is 0.35 or more? Okay, this is just a regular old normal distribution problem. Okay, so at this point it becomes just, you know, Z is equal to, you know, basically x minus mu over sigma. And in this case, the quantity that we're interested in is 0.35. What is the mean? 0.3, right? We said that p hat comes from a normal distribution, okay? Mean of 0.3, and our standard deviation is 0.045 826. Is that okay? Yes. Where did I get 7? This thing? This is, so this standard deviation is p times 1 minus p. P is 0.3. 1 minus 0.3 is 0.7. So I'm getting p 0.3 times 1 minus 0.3, which is 0.7. So 0.3 times 0.7 divided by n, 100, and I get this. Okay, so here I'm going to do 0.35 minus 0.3 divided by, whoops, let's close off our parentheses. I had 0.045826 in the answer before, and so if I plug that in, I get 1.09. Okay, I get a z-score of 1.09. My picture looks like this. I'm at 1.09. And I want to know how much is over here. Okay, so how do I answer this? Yeah, so I look up 1.09 in the table, and I get the area to the left is equal to what's that? 1.09 is 0.8621, okay. So that means this area over here is going to be 1 minus 0.8621. And I get, whoops, 0.1379. Okay. And so that's my answer, okay? So if we're taking a random sample of 100 pieces, what's the probability that we get 35% or more orange candies? About 14% here. So that is our answer. Just want to make sure that the question being asked makes sense. What we're doing makes sense. Okay, let me talk about the conditions, because we said the central limit theorem says, you know, the sampling distribution of p hat follows the normal distribution as long as certain conditions are met. Okay, so we'll talk about those conditions. I just want to make sure I'm caught up here. Okay, so we'll say conditions to use the central limit theorem. Okay, so number one, the sample must be selected randomly. Okay, and members of the sample must be selected independently of each other. what does it mean to select independently of each other? Yeah.
So you don't pick them out like right after another?
Yeah, I guess it means picking one person has no influence on whether or not someone else gets picked. Okay, so it's not like you're gonna take couples together. If you select one, you're not gonna select the spouse or something like that. You're selecting individuals one by one, and whether someone gets selected or not has no influence on whether another person gets selected. Okay, so if selecting one person neither increases nor decreases the chance that his or her spouse gets selected. Okay, that spouse could also be selected. Spouse might not be selected. Okay, the probabilities don't change. Okay, so usually if a sample says it was selected at random, it implies that it was selected independently as well. Okay, so if it says selected randomly, okay, that generally implies independence also. Okay, the second one is the sample must be large enough. Okay, you don't want a sample that's too small. If the sample is too small, it doesn't work. Okay, what large enough means is that n times p and n times the quantity 1 minus p must both be greater than 10. Okay, so your sample has to be large enough. Okay, or this is one way to check, or in the sample itself, there must be at least 10 quote-unquote successes and 10 quote-unquote failures. Okay, so again, the terms successes and failures are arbitrary. So basically, if we're taking pieces of candy, we need to have at least 10 that are orange and at least 10 that are not orange. Okay, if we happen to get a sample where we get 12 non-orange pieces and only 6 orange pieces, this sample is not big enough because you need to have at least 10 of either kind. Okay, so your sample must be large enough. So in some problems you're given p and n, so you have to check by doing the multiplication. In other problems you're not given n and p, you're given kind of the results of what you see in the sample. In that case, you just want to make sure you have at least 10 successes and 10 failures. Okay, and the last one is the population must be big. Okay, and what we mean by big is that the population must be at least 10 times bigger than our sample. Okay, or conversely, do not sample more than 10% of the population. Okay, and we can also say Okay, so these are the conditions that we have to check to make sure we can apply the central limit theorem. Okay, and what the central limit theorem, well, let's see if you guys remember. What does this? What's the big idea of the central limit theorem?
That the mean represents the data from the sample, represents the data represented from the population.
The big idea of the central limit theorem is that the sampling distribution of p hat follows a normal distribution. Okay, so all of that stuff we learned in chapter 6 about the normal distribution, we can apply that to sampling distributions, which, you know, if we think about it, is a rather remarkable outcome, right? You know, all we're saying is that we're just going to randomly draw samples out of this tub of Reese's Pieces candies, okay? You know, I don't know if it's intuitive to say, hey, this is going to follow the normal distribution and I can use this chart to make conclusions about that, okay? Intuitive or not, the mathematics works out that we can say this, okay? That if we repeatedly do this thousands of times, okay, p hat, that distribution of p hat follows the normal distribution. And because of that, we can then use, you know, our z table and answer questions such as, you know, if I draw pieces, 100 pieces of candy, what's the probability that it ends up being over 35%? We'll see. You know, it didn't end up over 35% this time, but it happens about, we said 14% of the time, okay? So, so you know, we can do that and do studies like that, okay? All right, so let's we'll try a few example problems here. Maybe I'll ask to see if the conditions are met or violated here, okay? So again, here are our central limit theorem conditions. We have random or independent sampling. 2 is large sample. And 3 will be big population. Now the book might write these in a different order, but these are essentially the 3 conditions that we have to check. Okay, so here's scenario A. Okay. Okay, so you know, we are curious of, you know, what percentage of people, we'll say of all people in the USA have a driver's license. Okay, so you know, we randomly select 25 people. Okay, 18 of them have licenses. Okay, are any conditions violated? So don't shout out your answers. Okay. I'll write these out. You can decide. Come to your conclusions. Don't shout out your answers. Okay. Okay. So we're gonna say, you know, we go to in elementary school, okay, there are 280 kids enrolled. Okay, we want to know what percentage of kids play after school sports. Okay, so we survey 40 randomly selected students, and we'll say 22 of them play sports. Okay. We decide to conduct a survey. Okay. We interview people. That we meet on the street and ask if they are registered to vote. Okay, we survey 60 people, and 41 of them are registered to vote. Okay, so we have different scenarios, and the question is, are any of these conditions violated? Are multiple conditions violated? Or are none of the conditions violated? Okay. So these are all situations where, you know, we are dealing with a sample and we're asking, we want to make conclusions about the proportion that exists in the population, right? Okay. All right, I'll give you guys another second to write these down and try to come up with your answers here. Okay, let's look at scenario A. We're curious what percentage of all people in the United States have a driver's license. Okay, what is the population in this scenario? The population? All people in the U.S. All people in the U.S., this is our population. It's a big population. It's like 300-something million people, okay? All people in the U.S., okay? What percentage have a driver's license, okay? That percentage, this is the P that we want to know about, okay? This is our P that we want to know about. All right, I have no idea what this number is, okay? All right, so what do? We've selected 25 people. This 25 people, this is our sample, okay? This is our sample, our N is 25. Okay? 18 of them have licenses. What's 18? Yeah, we don't have a letter for this. We might call this X, okay? X is 18. Our P hat would be what? 18 divided by 25, okay? Because in our sample, we looked at 25 people, 18 of them have driver's licenses, so we would do 18 divided by 25, and we get 72%. Okay? All right, let's check if any of these conditions are violated, okay? Was our sample selected at random? Yes, okay, it says we randomly select, so that condition is met, okay? Is our sample large enough? How do we check if the sample's large? We would need 10 successes and 10 failures, right? We have 18 of them have licenses, so that means 18 yes, so we have over 10 successes, okay, so 18 success. How many people don't have licenses? 7, right? Because we have a total of 25 people, right? So this 7 is not bigger than 10, okay? So our large sample condition not met, okay? Okay. Is the population big? Yes, it's all people in the USA. Okay, it's a big population. 300 million people. The only way we'd violate the big population is if we surveyed more than 30 million people, which we certainly will not have money to do. Okay, because every survey costs, takes time, and you got to pay someone to do that survey. So it's not going to happen. Okay, B. We go to an elementary school. Okay, there are 280 kids enrolled. We want to know what percentage of kids play after-school sports. We survey 40 randomly selected kids. 22 of them play sports. Okay, what is our population? Yeah, all the kids at the elementary school, right? So 280 kids enrolled, so our population is all kids at the school. What's our parameter that we are interested in? Yeah, the percentage that plays after school sports, okay? This is our parameter that we want to know. Okay, what's our sample? The 40 randomly selected kids, this is our sample. Okay, and 22 of them play sports. All right, so let's check our conditions. Was our sample selected randomly? Yes, it says randomly selected, so we're good there. Is our sample large enough? Yeah, we have 22 success. Okay, and again, the labels success and failure are arbitrary, okay? So 22 of them play sports, which mean 18 do not, okay? So those are both bigger than 10, okay? This is greater than 10, this is greater than 10, so large sample condition is met, okay? Is our population big?
No.
It needs to be 10 times bigger than our sample, right? So our population either needs to be over 400, 10 times 40, or our sample needs to be less than 10% of this, okay? So either we need to select less than 40 kids, like 28 or fewer, or we need over 400 kids. So big population condition is violated. Is that okay? All right, let's take a look at situation C. Okay, we decide to conduct a survey. We interview people that we meet on the street and ask if they are registered to vote. We survey 60 people. 41 of them are registered to vote. Okay, what is the population that we're interested in? Huh? That's not our... This would be our sample. The 60 people we surveyed would be our sample. Yeah, the population's not clearly defined. It just seems like, I guess, people. Our population is ill-defined as people. It doesn't say how we selected these people for our survey, okay? The 60 people we surveyed, this would be our sample. Okay. All right, let's see. Is our sample selected at random? No, it's not, okay? Because it says we interview people that we meet on the street, okay? I promise you that's not going to be a random sample, okay? Just because you have, unless you set up some kind of operation where you put yourself in random locations, okay? If I go out there, if I just go to some corner and I survey people I meet on the street, I'm only going to get people who live in that geographic area who happen to be walking on the street at that time of day, okay? So if I put myself there at, 10 a.m., I'm going to meet people who don't work in offices, right? Or I'm going to meet, whatever, okay? So depending on, what time of day you go out there, what street you're on, you're not going to get a random sample, okay? So meeting on the street, it feels like you're just meeting random people, but it's certainly not random, okay? So this is not a random sample. Okay, so, if your survey is not random, then really the other ones don't really matter, but we can check, okay? Large sample, yeah, that's met. We've got 41 who are registered to vote. We would have 19 who aren't, so that's met. Big population, because our population is so ill-defined as people, yeah, I guess it's going to be a big population. But, if you conducting an actual random survey is very challenging to do, okay? These different organizations that conduct polls, especially during election season, they're working very hard to try to get representative samples, but it's quite difficult to do. And so, if you guys were following the the politics before, like the Iowa caucuses, the polls had Trump leading, and then he ended up coming in second place, which was maybe a surprise or not, who knows. And that's just because, despite all of these different organizations trying to conduct surveys, it's hard to pull off, okay? And so, they happen to be surveying people, too many Trump supporters or whatever. Stuff like that happens. It's hard to get a truly random survey. Kind of the best method that people use is robo-dialing, which is not really a great method, but that's kind of the method that exists. But as soon as someone picks up the phone and hears like, "Can I take a few minutes to answer a survey?" some people hang up. Okay. And so you're automatically going to lose people who choose to hang up, and that may or may not be related to the survey question, right? If the survey question was, do you mind taking, this would be a ridiculous example, but if the survey question was, do you mind answering surveys over the phone, okay, you're only going to get people who say yes, right? And everybody else who just hangs up or avoids the call will not be surveyed. And so that's obviously not going to be a representative sample. Okay, why don't we take a 10-minute break here. We'll come back, we'll do another math numeric example to work through, and then we'll talk about more inference here.